All right, before we get started with today's lecture, I want to talk real quick about something else. For like registration for classes and all that kind of crap, as I'm sure most of you are aware of, started today. If you're planning on taking Dr. Chen's information theory class, you will need to go to forms.latech.edu and submit an add form for that. Because he requires a special permission signature to get into the class. So just list me as the advisor and I'll add you in there. If you are taking my ELEN 438 and 439 course, the way it was previously structured, 439 was offered in the spring. So it has 438 listed as a prerequisite instead of a co-requisite. So if you are planning on taking those classes, just shoot me an email and I'll send an email to the registrar telling them to add you into 439. If you have any other type of registration issues, generally speaking, you can just shoot me an email and we can resolve stuff fairly quickly. Okay, so for today, we are going to be talking about feedback systems. So give me a moment. Just make sure. Yep, just people saying that they're here. Okay. So why is this not showing the right thing on the screen? All right. So up to this point, we have been designing open loop amplifiers. And I feel that we have gotten pretty good at that. So that begs the question of why we would bother involving feedback into our amplifier schemes in the first place. So you guys have been dealing with negative feedback amplifiers since circuits 1. So do any of you guys have any reason why we've been employing negative feedback to the overwhelming majority of the amplifiers that we've dealt with prior to this class? Anybody have any idea why we do it? Any thoughts whatsoever? Stabilize the output. That is a very, very good one. So specifically, I might be putting words into your mouth here. But the open loop gain of an amplifier is dependent largely on the process and things like that. So that means that if there's any process variations like resistor mismatching and all that kind of good stuff internal to the IC, we could see that the open loop gain does not behave as we would expect. We can then use feedback to kind of correct this, which is called increasing the gain desensitivity or creating gain desensitivity. Another thing very specifically that we covered in electrical engineering 223, the open loop gain of an op amp in particular is usually on the order of a couple of 100,000 for a well-designed op amp. It could be lower, it could be higher depending on the process and all that kind of stuff. That very, very large open loop gain is effectively useful for, or useless for the overwhelming majority of circuits. Instead, we need to bring that gain level down to some manageable level. So that's another reason why we might do it. We can use feedback to increase the linearity, which is effectively what we just talked about. So extending the linear range of the amplifier. We could use it to extend the bandwidth of an amplifier, right? So we know that the gain bandwidth product should be constant. Well, the open loop gain is usually very, very high, but only for a very small bandwidth. So we can use a feedback system to lower the gain of the system, thereby increasing the bandwidth of the system. So all of the things that feedback does, it does at the expense of lowering the overall gain. So you lower the gain and then you get some advantage to doing that. So for a general negative feedback system, the structure is going to look something like this. And this is from control theory, so don't worry if it's kind of unfamiliar to you. We have some source signal, X sub S, that is fed into a mixer. The output signal of this mixer is fed into an amplifier characterized by an open loop gain of A1. And we're going to assume we have a unilateral system, meaning that the signal can only flow in one direction. And over here, we have our output signal, which I'm going to call Y for right now. And then we're also going to have a feedback network. And for a negative feedback configuration, where K here is what's known as the, let's see, what is the exact word I have? Feedback factor. It's also a unilateral system. We are going to wind up subtracting some portion of the signal from our input. So this is the general negative feedback system. I know that it doesn't look like anything that you guys have seen before, but we could actually map this one-to-one to an op amp, and we'll actually wind up doing that quite a lot. But I want to talk about some of the intermediate points in here and what's going on, okay? So the first thing that I'm going to do is I'm going to define the signal that is the true input to our amplifier. And I'm going to call that X sub I, okay? We will call this, or in control systems classes, this is referred to as the error signal, but we're going to kind of map things out a little bit as it goes through. So our input signal X sub I goes through our feed forward system, which is our amplifier characterized by A1. And so at the output, we have a signal Y is equal to A1 times X sub I. This output signal is sensed or measured. So we might call this portion of the circuit a sense mechanism. This could be as simple as an open circuit if we wanted to measure a voltage, or a resistor if we wanted to measure a current. So we could get a voltage, but we know that the current and voltage are directly related through Ohm's law. This sensed output gets fed through the feedback network K. Resulting in a feedback signal that is K times Y. And then this feedback signal is subtracted from our source signal, which is yields our input or error signal, XS minus X sub F. So this is what's called a signal flow diagram. This just circulates over and over and over again. We've talked about, let me write something here. This guy right here is commonly called the return mechanism or the comparison mechanism. All right. So notice that our return mechanism applies a negative sign when we add that source signal and feedback signal together. That is what is giving us negative feedback. So if we look at the transfer function for this guy, which is simply the relationship between the output y and the source signal that we are applying, y sub s, we can see just using a couple of steps of simple math here that the output y is equal to a1 times x sub I, which in turn looks like a1 times x sub s minus x sub f, which in turn is a1 times x sub s minus k y. And rearranging this, we get a transfer function, which I'm going to call AF, which is just gain, which we've always been calling with an A, and the F stands for feedback because the feedback loop is included. So it might also be called gain with feedback. Another thing that it's I've seen it called is the asymptotic transfer function, which is a little bit beyond the scope of this course, but it's got lots of different names that all means roughly the same thing. And for this general negative feedback system, where we define this as y over x sub s, it looks like a1 divided by 1 plus k a1, where, to be clear, a1 is the open loop gain of the amplifier, and k is the feedback factor. So we can see from this expression that our feedback network serves to lower the overall gain of the system, be it a voltage gain, current gain, transconductance gain, or transimpedance gain. We have our open loop gain divided by some factor that is 1 plus some other quantity. This quantity Ka has a special name we'll talk about in a little bit, but assuming that it's positive, our gain is reduced, and so we have achieved a negative feedback situation. All right. So let's talk now about our loop gain. Okay. So loop gain is the product of our feedback factor K and our open loop gain A1. And it is the characteristic parameter of a negative feedback amplifier. So it is the absolute most important thing to know. It is so important because its sign determines the polarity of the feedback. So what I mean by that is K times A1 must be positive for negative feedback, which you would think would be pretty easy to achieve, and in most cases it is, but we'll see even that if we have a system where we choose a resistor network or something like that, where it should be practically impossible to make it look like it has a negative loop gain at certain frequencies because of internal capacitances and things like that, we'll see that we get a 180-degree phase shift and make our system wildly unstable because we're accidentally applying positive feedback at those particular frequencies. So that's where our ability to analyze poles and things like that comes into a lot of play here in looking at the system stability and all that kind of stuff. Let's see. The magnitude determines how close the closed loop gain AF is to its ideal value. So if we have AF is equal to A1 over 1 plus K A1, right? What happens if we had an ideal amplifier? So way back from circuits 2, what was one of the constraints for an ideal amplifier? There were 3. Anybody remember any of them? Infinite input impedance, okay. 0 output impedance, infinite open loop gain. Right, so an infinite open loop gain. So as A1 goes to infinity, what does this reduce to? So let me scratch this real quick. Let's say the limit as A1 goes to infinity of A1 over 1 plus K A1 is what? 1 over K, our feedback factor, right? Where we're assuming that K times A1 is much, much larger than 1, which should be reasonable if A1 is infinitely large. So this is a very interesting revelation, okay? If we have an ideal amplifier with an infinite open loop gain, then the transfer function is dependent only on the feedback network that's applied, right? Which is exactly what we saw when we analyzed op amps in circuits 1, and what we saw when we analyzed negative feedback op amps specifically in circuits 2, right? It doesn't really require that A1 is infinitely large for this to work. A1 can be on the order of a couple of hundred and will still be within a few percent of an ideal configuration. So that's really good to know, because if we want to design a stable op amp with a stable transistor amplifier with a particular gain, we can actually get there just by applying a feedback network and then making a few subtle corrections here and there to account for some non-idealities. Another consequence of the open loop gain being infinite, which this again arose in circuits 1 and 2, but we called it a little something different. If we scroll up here, right, we can see that our feedback signal, XF, is equal to K times Y or K times A1 times XI, okay? So I'm just substituting Y is equal to A1 times XI here into Y. So if K is some finite number, A1 is infinite, and we expect our output to be finite, what does that imply about the size of our error signal? It has to be 0. Xi must be 0 if we have A1 times, so infinity times something equals some finite value, so some non-infinite value. The only way that happens is if our error signal is 0. We can mathematically see that pretty easily by saying that x sub I is, as A1 goes to infinity, the limit of x sub s divided by our feedback, or our amount of feedback, 1 plus k A1, will be 0. So this is what causes our voltage constraint equation in when we looked at a practical op-amp model with an infinite open loop gain. And we saw that the voltage present at the non-inverting terminal and the voltage present at the inverting terminal of the op-amp have to be equal to each other, or their difference has to be equal, because their difference is the error signal, right? So just another way of revisiting stuff that you guys have already taken care of. All right, this is what's responsible for increasing the linearity, which we'll talk about in much greater detail on Wednesday. One of the last things about the loop gain is that its magnitude determines the amount of feedback which doesn't have a particular symbol, but it's just that factor 1 plus k A1. And as we'll see later, the magnitude, I can't write the letter A today, of the performance improvements incurred by using feedback. And lastly, and this will be one of the last topics that we talk about in this class, its value is directly related to the system stability. All right, so because the loop gain is such a critical parameter, it's probably fairly useful to know how to calculate it. All right, so we are going to talk about a method by which to do that. All right, it is a 3-step process. The first step is to set x sub s equal to 0. So we're looking at this thing while we're looking at our feedback system or our feedback amplifier while we are applying no excitation to the system at all. Our next step is that we need to break the feedback loop at a location such that terrible. K and A1 are unaffected. So we can't break the loop somewhere that would cause A or K1 to, or excuse me, A1 or K to change. So typically speaking, here is our 0 applied for X sub S. Here is A1, again, assuming the unilateral system. So we might break it here. Like so. And then what we will do is we will apply a test signal, X sub t, to the input of our loop, so the input of the feedback system. And determine the return signal, X sub R. So we'll measure X sub R at the output of the amplifier. Okay. So if we just analyze this simple loop, we can actually get a pretty reasonable relationship. X sub R, we can see here that X sub F is just going to be K times XT. X sub I is then going to be negative K XT. And from that, X sub R is going to be negative K A1 X sub T. And so our loop gain KA1 is simply negative X sub R sub T. Right? So it's the loop gain, which is really just the product of the feedback network and our open loop gain, because that's the gain we observe if we pass a signal around the loop with nothing external influencing anything. Okay. So I have a few examples prepared, and then that'll wrap things up for today. The first of which is a simple op-amp circuit. Where hopefully we will see the one-to-one relationship between the general feedback structure that we discussed before and the circuit parameters. So let's say that we have the following circuit. V sub S, R sub S, Here is our amplifier that has an open loop gain of A1. So this is obviously our feed forward system. This wire constitutes our feedback system. This resistor RL is really our sense mechanism. We can think about it. And this voltage here, the difference between this point and this point is our error signal. We're not going to really see much of a signal X sub F because we have a short circuit in there. So let's say that assuming that the op amp has an infinite input impedance and 0 output impedance, what is our feedback factor? Okay. Anybody got any ideas, just looking at this thing, what you think the feedback factor might be? So what kind of amplifier is this? Let's start there. A unity gain buffer. So intuitively, it feels like it's probably going to be 1. That is exactly right. We'll mathematically prove it in a second. But I just want you guys to understand the stuff that we've learned prior is absolutely applicable to something like this. Okay. So the second thing that we're going to investigate is if instead A1 is equal to 1,000 volts per volt, which would be a very, very low value for the open loop gain of an op amp. What is the value of the closed loop voltage gain AF and the amount of feedback 1 plus K A1? All right. So using the practical op amp model, our system looks something like this. Here is our voltage, VI. I'm breaking my feedback loop. So this is where I'm applying X sub T. We know that we should have our open loop gain times our differential voltage. So this is just A times VI. Here is my return signal, X sub R. And here is RL. And here is my output voltage, which is the exact same thing in this case as my return signal, right? So if I applied some test voltage V sub T or X sub T or however the hell you want to call it, I've been using X and Y's because they can stand for current or voltage. But let's just say specifically that we're going to apply a test voltage to V sub T. What should we see at our output? Anybody got any thoughts? So what does our output signal by definition have to be because of the structure of this guy, where we have assumed 0 output impedance and infinitely large input impedance. It's not a trick question. A1 times VI, yeah, okay. There's nowhere for a voltage drop to occur that would change that relationship, right? So we know that X sub R is equal to A1 times VI. What is the relationship between VI and X sub T, our test signal? Negative XT, right? So positive. So if we consider this to be a nodal voltage where we're applying the positive polarity terminal to that node that I have X sub T aligned with, and the negative polarity terminal at ground, we see that it is exactly equal to negative VI. Excuse me, VI is equal to negative X sub T. And so from this, negative X sub R over X sub T is exactly equal to negative A1, which implies then that K is equal to 1, right? That's correct, yes. So that is absolutely something that I needed to do there. Yeah, let me specify that because that is the first step of this. Thank you. So if I ground that guy, it should be, now it should be hopefully much more obvious to see that X sub T is exactly equal to negative VI and vice versa. Thank you for pointing that out because that was a necessary step. Yes, ma'am. So if we put RS right here, great question. What current flows through it? None. So it does nothing. So that's fantastic. Yeah, Brian. Let me, hold on. I see there's a sign issue here. This is where my inexperience with stuff might crop up and bite me in the ass. So let me look at my, where's my definition? Just go, okay. So K times A1. All right, let's erase this real quick. Okay, so if I have this expression here, XR over negative XT is equal to A1, right? So there shouldn't be an extra negative sign there. Which, that ratio by definition is K times A1, which implies then that K is equal to 1. So I mistakenly put an extra negative sign in on the right-hand side of that equal sign, because K times A1 should be negative X sub R over X sub T. So hopefully that clarifies things. I apologize for my mistake. All right, so from this is our solution for part A. For part B, things get a little bit easier because we can just throw stuff directly into our equation, right? So A sub F is equal to A1 over 1 plus K A1, which is 1,000 over 1,001, or 0.999 volts, right? So we're very, very close to the ideal value of 1, which is what we would expect for a unity gain buffer. I don't remember if I derived this in circuits 2 for you guys, or I might have derived it earlier in this class actually when we were talking about op-amp circuits. But I definitely do it now in circuits 2, and this is the result that you get by analyzing this guy as a circuit with a finite open loop gain. Excuse me. So for our amount of feedback that we are applying, which is 1 plus KA1, this is obviously then 1001. Has a value of 1001, and we could consider it to be volt per volt. Wouldn't be an issue there. This amount of feedback applied number right here, 1001 volts per volts, really doesn't mean a whole heck of a lot right now. But what we are going to observe on Wednesday is that when we have a system like this with negative feedback applied, what's actually happening is that if we had some finite input resistance, Rn, applied across the terminals where Vi is located, the amount of feedback applied scales that value by that factor of 1001, okay? Similarly, if we had an output resistance between this node of our dependent source and our output terminal, it will scale that output resistance by a factor of 1 over the applied feedback. So what happens with negative feedback when we have finite input impedances and finite output impedances is that the input impedance gets scaled by the amount of feedback, scaled up by the amount of feedback, and the output resistance gets scaled down by the amount of feedback, which is something that we actually observed way back in circuits 2 when we were looking at the input and output resistance of an op amp when we were using the practical op amp model, that kind of stuff. So like in an example that I work in circuits 2, we see that for an input resistance of 100K or 150 kilo ohms or something like that, we wind up seeing an input resistance from the perspective of the input voltage source of somewhere around 5 mega ohms. And similarly for an output resistance, having a value of 25 ohms, from the perspective of the output terminals of the op amp, it actually looks like less than a single ohm. And it's because of this feedback scaling that causes that to occur. All right, so let's look at something a little bit more in line with this class. This one we're going to look at more so qualitatively because it does not, the circuit itself does not easily transfer to our traditional signal flow diagram that we looked at just a moment ago. So I would argue that based on the behavior of this circuit, a common emitter amplifier that features emitter degeneration behaves like a negative feedback amplifier, okay? Now, you may look incredulous, and that seems perfectly reasonable to me, because if you asked me where to define the feedback loop for this guy, I couldn't do it. I literally tried this morning to work it out mathematically so that we could break the circuit and all this kind of stuff, and could not get the results that I want. But its behavior exactly follows that of a negative feedback amplifier. So I'm just going to redraw this guy slightly for our small signal model. Here is RC, here is V out. Here is RE. And I think it is a question of defining what we want our output signal to be that is problematic here. So I am explicitly, what's up? So I could, what you're suggesting is this. These 2 points are connected, and we can see that a current circulates around the circuit in this direction. You're 100% correct there. Okay. What I'm saying is I couldn't make the math work when I tried this exact thing. Now, it was 4:30 in the morning, so there's a distinct possibility that my brain just wasn't working correctly yet. So still, we're going to analyze it qualitatively, okay? So what happens in this circuit if RE is short-circuited? Thoughts? What is the relationship between our input current and, or excuse me, our input signal, which is Vn, and what I'm calling our output signal, IC? Because this is a transistor-based circuit, right? So inherently, transistors convert an input voltage into an output current. So if Vn increases, and we have Re removed, if Vn increases, what happens to IC? Its magnitude increases, right? Can the magnitude of IC increase indefinitely? No. Why not? Sorry, I heard something about the wire and then something about the lambda effect. Let's throw away the early effect. Let's say that it doesn't matter. Why can't the current increase forever? Let's not worry about that physical restriction of the wire ampacity either, okay? As IC increases, the current through RC increases, right? Well, as the current through RC increases, that means the voltage drop across RC increases as well. But we have a limit of the maximum voltage drop that could ever occur across RC. It's got to be VCC at its maximum. So we'll see that as Vn increases, IC is going to, or the magnitude of IC will continue to increase until saturation occurs, right? Which is the whole point of when we first started talking about BJT amplifiers and put constraints on the size of that resistor and or the size of the biasing current, right? So IC increases until saturation occurs, which effectively breaks our system. It's not behaving the way that we intend it to. Now, at the small scale, for this open loop system, our gain, IC divided by Vn, is simply the transconductance, and our voltage gain, AV, is negative GM times RC. So that resistor RC is really nothing more than the sense mechanism that allows us to view the output signal, okay? With our resistance RE included. Let me just ground this guy right here, right? All right, so if we apply an increasing, or we have some voltage Vn and we apply an increase, this quantity goes up. The magnitude of this quantity goes up, but the magnitude, let me just write this right here. Of this quantity also goes up. So right now, it's not looking like we have a feedback system, or if we have one, it's looking like positive feedback. But what happens to our base emitter voltage, VBE, as VRE increases? It has to go down, right? Because we can see, obviously, that VN has to be equal to VBE plus VRE. So if VRE goes up, VBE has to go down to accommodate it. So this quantity decreases. What happens when the base emitter voltage in a BJT decreases? IC goes down. So we have a negative feedback system, right? Our input signal is pushing things up, but this is our return that's creating our error signal, causing the output to go down. If we look at the gain of this system, the overall voltage gain is negative GM RC over 1 plus GM RE. So we can see pretty easily that neglecting the effects of our, sorry, this should be AF, of our sense mechanism, which is our resistor RC, this system has a closed loop gain of positive GM divided by 1 plus GM RE. So that resistance RE, the value of that resistance is the feedback factor for this system. It's causing it to behave as if it were a negative feedback amplifier. So again, I 100% agree that it is not intuitively obvious to look at that circuit and say, that looks like it's got feedback, but it certainly behaves like it does. So let's look at a more complicated transistor model, but one in which we can actually kind of see that feedback is occurring and apply a more traditional method of solving it. So let's say that VDD is here. I have some resistance RD1 like so. I'm going to have some resistance RD2 here. This is going to be transistor M2. This is where I'm going to take my output. I have some transistor M1 here. I'm going to call this guy resistor R1. And I'm going to tie these guys together with a resistance R2 here. And this is where I'm going to apply my input. I'm going to explicitly show where my error signal is generated, just like before. It's the voltage drop VGS of transistor M1. This is my feedback voltage, VF, the drop over R1, which is similar to the voltage drop over RE in our last example. And Vn is obviously substituting in for Vs. Vout is substituting for Y, right? And to make our life easier, lambda 1 and lambda 2 are 0. So we're not going to have to worry about channel length modulation. Our goals are to determine K and the ideal value of our transfer function, which is just 1 over K, so that's fairly trivial. And I would like to determine our loop gain, KA1. So when we looked at that op-amp circuit a little while ago, we had a fairly intuitive understanding how this stuff worked. What's up, Sam? Oh, great question. It's grounded. A fantastic question. Yeah, definitely needed to include that. It wasn't just some floating potential doing whatever the hell it felt like. All right, so as I was saying, our first example that we looked at was a simple unity gain buffer where we kind of intuitively knew what was going on. I would argue that we don't have any intuitive idea what the hell is going on with this guy. We have no idea what our open loop gain is or anything like that because we haven't really seen many circuits like this, right? So what we are seeing, transistor M1, we apply some input signal, which is going to cause some collector current to flow, which is going to cause a voltage drop over the resistor RD1, creating the bias point for transistor M2, which then causes some current IC2 to flow, causing a voltage drop over resistor RD2, which is establishing our output, which is fed back through that resistive network, and all that kind of stuff. So we can talk about what's happening, but it's hard for us to quantify what's happening, okay? So one means by which that we can determine the feedback factor of this guy is to just say, what if the open loop amplification was infinitely large? So what if our amplifier was ideal? That will allow us to determine our feedback factor for the system. So the question that you might be asking yourself is, well, how do I accomplish that feat? In practice, all we really have to do is just pick one of our two transistors. I'll do it for transistor M1 because it makes the math a little bit easier, and just say that its gain, which is GM times VGS1, or well, I guess that's not really its gain, but we are effectively scaling that source to be infinitely large, okay? Or we're scaling that transconductance to be infinitely large, which means if we have an ideal system, what does our error signal have to be? 0. So if this guy right here is 0 volts, I'll do this in a different color so it's obvious what we're talking about is something new. For an ideal system, our error signal is 0 volts. What does that tell us about our drain current for that transistor? It has to be 0 as well, right? Because VGS is less than the threshold voltage. If VGS is 0, which is our error signal here, then the current flowing through has to be 0. Our feedback coefficient, K, if we looked back at our original network, let's just do that real quick. So we have here XF is equal to K times Y. So I would argue that K should be XF over Y. I thought it would be the other way around. Yeah, why do I have it the other way around? I don't know. This signal Y gets multiplied by K. This is what happens when it's the first time teaching something. All right, so let's just say that XF is equal to K times Y, which in this case, if we move things around, K would be equal to XF, so that is our voltage, VF, divided by our output, VF. I'll have to look into that. We can pretty easily, I hope, develop a relationship between VF and Vout, right? If we know that this current that I have in orange, my drain current through the transistor is 0, I have a simple voltage divider network that relates VF and Vout, right? So I could say that Vout is equal to R1 over R1 plus R2 times VF, which means that Vout over VF is equal to just R1 over R1 plus R2. So our feedback factor then looks like the reciprocal of that, which is just 1 plus R2 over R1. Brian, you look confused. Did I do it wrong? You are 100% correct. Yes, I did voltage division wrong. The person that taught this to you guys multiple times totally biffed it. VF, Vout, which means okay. So that's all still correct then. So I divide both sides by Vout, giving me that. I still get R1, VF, the resistance over the and total series resistance. Okay. Then VF over Vout is R1 over R1 plus R2. Okay. Are we in accord? All right. I apologize. Okay. From this, our ideal gain is 1 over K, which is just 1 plus R2 over R1. So even though everything other than these two resistors looks wildly different than a non-inverting op amp, from the ideal case, this is exactly how it's feels. Now, let's talk about figuring out what the loop gain is. This is where I'm a little bit more confident. Okay, so to find KA1, we set Vs is equal to 0 and break our feedback loop. And I am going to break the loop at the place where I found the math to be the easiest. So I'm going to break that connection between the drain of M1 and the gate of M2. So that's where my return signal X sub R is going to be measured at. Over here is where I will apply my test signal X sub T. This is RD1. This is RD2. I'm remembering to actually draw the ground connection for transistor M2 this time. I have my resistor R2 that goes here. I have my resistor R1 that goes here. And then I ground my input. So I've broken it up. So now let's talk about what happens when I apply my test signal X sub T, which in this case will probably be a voltage because we're dealing with a transistor. So if I apply some voltage to the gate of transistor M2, it stands to reason that I would observe some current ID2 flowing through that transistor, right? Assuming that my test voltage is large enough to overcome the threshold voltage of the transistor itself. So I can say that ID2 is simply GM2 times X sub T, or V sub T if you want to explicitly state that it's a voltage. Everybody okay with that simple relationship? That is the transistor doing exactly what it's designed to do, converting an input voltage into an output current. So now, some portion of that current ID2 is going to branch off and flow through that resistor RD2, and another portion is going to flow through the feedback path. And I'm going to call that current IX. And I want to pay attention to what's going on here, right? I have effectively a known amount of current leaving that node at the drain of transistor M2. That current sees a resistance of RD2 looking up, and it sees a resistance of R2 in series with the parallel combination of R1 and 1 over GM1. So I can use simple current division to tell me how much of that current branches off. Does that make sense? Okay. So I can say that IX is equal to negative ID2 because the current flowing in the opposite direction is what I would expect for a current divider. And to not have to deal with pesky reciprocals, I'm going to do the alternative relationship. So it's the resistance I don't want in the top divided by the total parallel, the sum of the parallel resistances seen. So that's going to be RD2 divided by RD2 plus R2 plus R1 in parallel with 1 over GM1, where, to be clear, if we look in this way, we see 1 over GM1, which is exactly what we did in class on last Friday, I believe, a couple of different times. So. That current IX splits, right? So we have a known amount of current flowing through resistor R2, which I've called IX. and then it splits because it sees, looking down, the resistance R1, and looking up, the resistance 1 over GM1. So applying another bout of current division, we get ID1 is equal to IX multiplied by R1 over R1 plus 1 over GM1. And finally, our return voltage, X sub R, is going to be what? Just ID1 times RD. 1. If I combine these four equations together, I find that negative XR over XT, which is, by definition, my loop gain, comes out to be GM1 RD1 times GM2 RD2 times 1 over 1 plus GM1 R1 times R1 over RD2 plus R2 plus R1 in parallel with 1 over GM1. So once we found this loop gain, we could then find the overall transfer function for the system, which in my opinion, this might be actually easier than analyzing the whole thing and trying to find the V in V out relationship. All right, so that's all. Oh, it's 10:45, so class is supposed to be over anyway. All right, well, that's all I have for today. So I think this might be the first time I actually finished not early and not late, so that's something new. On Wednesday, we are going to talk about the improvements to system performance caused by negative feedback. So we're going to mathematically define gain desensitivity, bandwidth extension, linearity improvement, all that kind of good stuff. If you have any questions about any of this stuff, feel free to shoot me an email. If you have any questions about any of your registration problems and all that jazz, you can also shoot me an email. I will catch you guys on Wednesday. Thanks.